So the sum and difference formulas are all summarized here in this definition box, right? And well, so those are formulas that of course you have to memorize for the exam, not the upcoming exam. Actually, I believe that's just going to be final exam material. All right, well, to see a little bit of pattern recognition, well, the sign formulas, notice we have a plus, that plus remains the same a plus, that minus remains a minus, and well, we have sine cosine and then cosine sine. Sine u cosine v plus cosine u sine v, and the same for the opposite in sine. For the cosine functions, we have cosine of the addition of angles of a sum of angles, but that one becomes a difference here. And as opposed to having product between sine and cosine for the sine function, the sine formulas, we have product of cosines minus products of sines. And here for the difference, which becomes a plus, we have a product of cosines plus a product of sines. Just so you can see the differences between the formulas, how do they change for their sign, and how are they different, the sines and the cosines ones. The tangent formulas, well, we have an addition or a subtraction depending on what do we have initially, all right? And then the term in the denominator changes the sign to the opposite of what we have, and that's 1 plus the product of the tangent. So of course we're going to see this in action by evaluating some quantities here. Well, let's do a little bit of a prep here before getting into finding the exact value. So the idea here is to write these angles that are not in the unit circle, that are not usually in the unit circle. So we can write them as either sums or differences of known angles or special angles. For example, the 15 degree. We can write it as a sum or a difference of angles. Well, we can write 15 degrees like this. Check this out. 15 degrees equals to 10 plus 5. All right? However, in this case, none of these two angles, 10 and 5, are nice angles from the unit circle, so this is not going to work. However, in this case, how about we use the difference? We use the difference instead. How about instead 45 degrees minus 30 degrees? And that's going to do it because we have angles for which we know special values. All right? And okay, what about 105? For example, 105 degrees. That's, for example, 90 degrees plus 15 degrees. All right? However, only the 90-degree angle is a special angle. However, the 15-degree, well, that's the same story as before. And in this case, well, you don't want to write it as a sum of 3 angles. No, just a sum of difference between 2 angles only. I mean, not 3, only 2. So this is not going to work. However, we could rewrite the 105 degree. How about 135 degrees minus 30 degrees? And those two angles, 135, are the same as what is that? As what's going on over there? Oh, those two words.
It's Explorer CSV.
What is that?
Explorer CSV.
Oh yes. Okay. And well, so we will be able to write it like this, right? We have to choose Friday, right? Anyway. What about, oh, careful, when it comes to radiant angles, those are going to be a little trickier to do because I guess when it comes to degrees, it's easier to see those numerical values and it's easier to break them up. All right, however, there's a bunch of ways that we can do to break up the 7 pi over 12. Well, number one, 7 pi over 12. One way is to do half about pi over 12 plus 6 pi over 12. All right, the 6 pi over 12 reduces to pi over 2, which is a 90-degree angle. However, the pi over 12, no, that's not one of those elementary angles that we know, pi over 3, pi over 6, or pi over 4, or any of their multiples. So we need to find another way. So what we're looking here is for a pair of numbers that are either pi over 3s, pi over 6, or pi over 4s, or their multiples. So, and this is a little tricky. Well, we need to explore many different ways here. Another way I could think of, I did 2 pi over 12. Let's do 2 pi over 12 plus 5 pi over 12. All right, 2 pi over 12, that's pi over 2 that we already got, but that's not going to work. Well, that's going to work actually, but not 5 pi over 12. No, so we need to find another way. Okay, let me go with 3 pi over 12 plus 4 pi over 12. How about that one? 3 over 12 reduces to, is that pi over 4? And 4 pi over 12, that's a pi over 3. All right? And these are two elementary angles that are from the unit circle, right? All right. So let's apply this to finding cosines of 15, sine of 11 pi over 12. Okay, so cosine of 15. Well, we already worked the cosine of the 15-degree angle, so no need to do the whole thing again. We can use the one we got from the basic idea. So that's cosine of, what's that? 45 degrees minus 30 degrees. Well, now check the form that we're going to use. We're going to use the cosine of a difference of angles, all right? So cosine of a difference of angles, let me highlight the formula that we will use, which is this one right here. Cosine of u minus v, which is equal to cosine u cosine v plus sine u sine v. Where in this case, if we adapt this formula to our exercise here, to our problem, we can label this as our u, and this 30 degree as our v. So if we use this formula, we can write this as cosine of 45 degrees minus 30, times cosine of 30 degrees plus sine 45 degrees sine 30 degrees. And well, I guess we can evaluate these four quantities from the values we know from the unit circle. That is, for cosine of 45 degrees, that's a root of 2 over 2, times cosine of 30 degrees, which in this case is root of 3 over 2, plus sine of 45 degrees, that's root of 2 over 2, and that's sine of 3, which is 1/2. And all we have to do is simplify each fraction and then combine them together. Usually for these kind of problems, we will get already a common denominator. So let's see. So that's root of 2 times root of 3. That's over 4 plus root of 2 times 1. That's root of 2 over 4. But root of 2 times root of 3, that's the same as root of 2 times 3, which is root of 6 plus root of 2 divided by 4. And that's final answer. So we're going to be asked to express this in terms of an exact answer. Root of 6 plus root of 2 equals to 4, not decimal. So of course it could be really easy to just go to the calculator, evaluate it in degree mode, and get a decimal answer. But we want this in terms of radicals. All right, letter B. Sine of 11 pi over 12. Okay, sine of 11 pi over 12. Again, this is going to be a little tricky. Sine of maybe a sum or a difference. Well, can we think of a sum, of a good sum or a good difference that we can get an addition up to angles that are pi over 3, pi over 4, pi over 6, or multiples of them. Well, let's see. How about 2 pi over 12 plus 9 pi over 12? Well, that works as pi over 2, and that's 9 pi over 12. That reduces to 3 pi over 4, which are both okay angles, right? So that's one way to go about it. However, I think I'm going to go with an easier way this time. I'm going to go, how about instead of 2 plus 9, how about 3 plus 8? That also works. 3 pi over 12, that's a sine of 3 pi over 12, that's pi over 4, plus 8 pi over 12, that's 2 pi over 3, right? And that's much better than the other version. If you do the other version, it's okay, it's fine. It also works. And let's use the addition or the sum formula for the sine function. And then let me highlight that formula. That's a sine u plus v. Okay. Actually, I don't want to scroll up and down every time. I'm going to rewrite the formula. So let me write it. Let me write it here. So that's sine of u plus v equals sine u cosine v plus cosine u sine v. All right. So let's use this formula. That's sine of pi over 4 cosine of v, which is 2 pi over 3, plus cosine u, which is cosine of pi over 4 sine of 2 pi over 3. Okay. At this point, hopefully we are a little more fluent with the values of the unit circle, or at least know that these values are going to change their sign based on the quadrant that we're working on. Well, pi over 4, that's an angle in the first quadrant, so all trig functions are positive, right? And well, for pi over 4, that's root of 2 over 2. Cosine of 2 pi over 3, well, cosine is negative in the second quadrant because 2 pi over 3, it's an angle in the second quadrant, and that's negative 1/2, and then plus cosine pi over 4, which is also a positive root of 2 over 2, times sine of 2 pi over 3. 2 pi over 3 has the sine function as positive in the second quadrant. That's root of 3 over 2. And same, negative times a positive. Careful here. That's going to be negative root of 2 over 4 plus, again, root of 6 over 4. And if we put them together into a single fraction, I would rather write the positive term first and then the negative. Root of 6 minus root of 2, the whole thing divided by 4. All right? So there's a couple of examples. One of them in which we work on an angle in degree mode, which is easier to play with numbers in degrees. However, when it comes to dealing with this in radian mode, it's a little tricky. If I were to give you an advice, and you don't have to do this, I mean, if you're okay with playing with the possibilities here, 3 and 8, 2 and 9, etc., that's fine. Another way would be to convert this angle in degrees, break it up in degrees, convert those two values back to radian, and then evaluate all those values using the unit circle the same way we did. That's another way. That's a possibility. Another possibility that if you want to explore, that's fine. I mean, you wouldn't be making anything weird, anything illegal. You wouldn't be coming up with new rules, right? So that's fine. Okay. How about we do a backwards type of problem, and let's see what we get. So let's see what we have. We have sine of 25 degrees times cosine of 35 degrees minus cosine of 25 degrees times sine of 35 degrees. Well, neither 25 degrees nor 35 degrees are nice values from the unit circle. All right? So, but check the pattern here. This looks like this. Check this out. This looks like sine u cosine v minus cosine u sine v. And if we were to adapt this to a formula that like the ones that we have at the top, okay, sine, cosine, cosine, sine, sine, cosine, cosine, sine. However, in this case, the one that looks like it is the difference, the difference formula in this case. Actually, you know what? There's a little typo here. I meant to write positive here, right? So those of you who have the PDF file, change it to a positive. Otherwise, it's not going to work. All right? So that looks exactly like sine of the sum u plus v. Well, so that means sine, in this case, of 25 degrees plus 35 degrees, which is sine of 60 degrees. And 60 degrees is what? Sine of 60 degrees is simply root of 3 over 2. That's a value that we know from the unit circle already, right? Again, this is about using these identities forwards and backwards, and so now we're going to apply this to find exact values of trigonometric functions given some information. Okay, so find the exact value of cosine of alpha plus beta, given that sine of alpha equals negative 4 over 5 and sine of beta equals negative 5 over 8. Given that alpha is in quadrant 3 and beta is in quadrant 2. All right? So now, just to give you the heads up of how you can see this worded differently, sometimes they can tell you that alpha being between, okay, quadrant 3 means going between pi and 2 pi over, or 3 pi over 2. And quadrant 2, that means beta varies between, or is between, what's that, pi over 2 and pi. All right? So, how are we going to do a problem like this? Well, number one, let's use the information that we have one at a time. Let me rewrite this. Sine alpha equals to negative 4 over 5. And cosine over here, beta equals to negative 5 over 8. So from here, we are going to construct two different triangles. One triangle for alpha and one triangle for beta. And in this case, they're asking us to have the first, or the alpha angle in the third quadrant. That is, okay, let's draw a Cartesian plane first. And draw a triangle, and well, this is going to be our alpha angle. And well, here is where SOHCAHTOA comes into play. That is, so sine, which is opposite over hypotenuse, opposite is negative 4 and hypotenuse is 5. Recall that the hypotenuse is always positive. All right? And well, if you look at the opposite side, that's a y value or a y distance in the negative direction. It's going down, so either way we can see it. And also on top of that, the sine function happens to be negative in the third quadrant. So there's a bunch of ways to make sense out of this idea and check the consistency of it. So we're missing one side. That is the adjacent side. So we're going to use Pythagorean theorem. For that, that's r squared equals x squared plus y squared. And well, r squared, that's a 5 squared equals x squared, which we don't know, plus b squared, or rather y squared, that's a negative 4 squared, which is 25 equals to x squared plus 16. And then let's solve for the x squared term. That is x squared equals 25 minus 6, that's a 9. X equals plus or minus the square root of 9, which is the square root of 3. However, we need to be careful because we need to choose the correct value. We get two equations because, I mean, two results because we got a quadratic equation, and the most natural thing here is to obtain two solutions, one positive, one negative. All right. So in this case, we need to keep the result that makes sense, makes the sense of direction of what we have for our triangles. And in this case, we have x going in the negative direction. That's going to be -3 then. Let's do the same thing for the cosine beta. For the beta angle, they're telling us to go with the second quadrant. All right. What about it? Okay, let's draw a Cartesian plane first and draw a triangle and represent the angle beta here. Well, SOHCAHTOA definition for cosine, that's adjacent over hypotenuse, where in this case the adjacent is -5 and the hypotenuse equals to 8. And well, so we're missing the opposite side. So we're going to use again the Pythagorean theorem. That is r squared equals x squared plus y squared. And r, which is given, which is 8 squared equals to x squared, which we are given actually. That's, oh, come on. I don't know why is that not working. It doesn't let me erase here. Oh, I got it. So 8 squared equals to -5 squared plus what's that? Y squared. That's a 64 minus 25 equals to 25 plus y squared. And well, let's solve for y squared first. Y squared equals to 64 minus 25, which in this case that's 39. And y equals to the square root of 39. And well, usually we simplify these radicals right here, and like for example, just so we can find, by finding actually a perfect square that can be taken out of the radical. However, even though 39 it's a composite number, that's 3 times 13, but none of those numbers are perfect squares, so we're going to leave it like this. All right? So that's the square root of 39. And well, I think we have all the information that we need, because now we can evaluate cosine of alpha minus beta. That's cosine alpha, cosine beta, minus sine alpha, or rather plus, the minus becomes plus, sine alpha, sine beta. Well, so we are going to get these trigonometric functions based on our triangular settings here. Okay, cosine of alpha, we're going to go with the alpha triangle. Cosine, which is adjacent over hypotenuse, that is -3/5. Cosine of beta, okay, cosine of beta, well, that's actually given. That's -5/8. And then plus sine alpha, let's go back to sine alpha. Oh, sine alpha, it's given. No need to do the opposite over hypotenuse thing again. So that's -4/5 times sine of beta. Sine of beta is opposite over hypotenuse. That is the square root of 39 divided by 8. And well, this is positive, so negative times a negative will be a positive. That is 3 times 5, which in this case is 15/40, plus 4 times root of 39, that's just 4 root of 39, or rather minus. And divide that by 40 also. Since we have the same denominator, how about combine this into a single fraction? 15 minus 4 root of 39/40. All right. Okay, so let's see what's next. Okay, example number 3. Find the exact value of this humongous madness here. Cosine of inverse sine of 2/3 plus tangent inverse of. negative 3/4. Well, you might remember how actually we evaluated. Okay, let me cover something here. We evaluated something like this, you know. Oh no. Let's ignore that last term. So we already evaluated something like that in the previous chapter, or rather section, not chapter. But it was about combining trigonometric functions with their inverse, composing more properly said. And well, so we're going to treat this the same way if we, for example, this time I'm going to highlight the first term. All right, I'm going to highlight the first term, and I'm going to highlight the second term using a different color. So, and I'm going to call this alpha, and I'm going to call this beta. Okay, that means I'm going to rewrite this as a cosine alpha plus beta. All right, and well, how about we relate the following quantities? This quantity, inverse sine of 2/3 with alpha, and inverse sine of tangent with beta here. And I'm going to write a couple of expressions on the side. Number one, well, actually not alpha, not beta. Actually, never mind. No, it's u and v. Cosine u, cosine u plus v. This means, on the one hand, that u equals to sine inverse of 2/3, and applying the inverse properties or the inverse functions properties, that means take the sine on both sides. That's a sine of u equals to 2/3. On the other hand, I'm going to use tangent inverse as our v, negative 3/4, and tangent v equals to negative 3/4. Okay, so from here we are going to construct another pair of triangles based on the information that we have for these trigonometric functions. All right, so number one, I'm just gonna go, well, yes, that's fine. Sine, is that sine? Well, anyway, so sine inverse of 2/3. I'm just gonna go with a triangle for u in this case, and well, sine which is opposite, that's a 2 over hypotenuse, which is 3. How about we use Pythagorean theorem to find the missing side? So that's r squared equals x squared plus y squared. That's 3 squared equals to u squared plus, no, not u squared, x squared plus 2 squared. That's 9 equals to x squared plus 4, and x squared equals 9 minus 4, which is 5. That's x equals the square root of 5, plus or minus the square root of 5. And we can go either way. I mean, we can go with the positive because of the orientation here of the triangle that we did. Now, it's going to be a little different for the triangle we're going to do over here. So, in this case, let me do another triangle that is opposite over adjacent, because that's the SOHCAHTOA definition for the tangent function. Well, so in this case, one of them is negative and the other one is positive. We have a couple of possibilities. Number one, to give y the negative sign and the x the positive, or vice versa, give the y the positive and the y the negative. I'm going to go with y being negative. If y is negative, well, x is positive, y is negative. The triangular arrangement would look like this, and the angle will be this v, where the opposite, which is negative 3, and the adjacent, which is 4, let's find, in this case, the hypotenuse of the triangle. That is r squared equals to x squared plus y squared, and that's r squared equals to 4 squared plus negative 3 squared. That's a 16 plus 9, which is 25, and the square root of 25 equals to 5. Although there is a plus minus technically, but again, keep in mind that the radius of the circle or the hypotenuse of the triangle is always positive, always taken as a positive. And I think we have all the information that we need to compute this value. All right, so that is cosine of u plus v, that's a cosine u, cosine v, minus, the plus becomes a minus for the formula, sine u, sine v. And that equals, well, in accordance with our setting here, okay, let's go with the u angle. Cosine of u, so that's adjacent over hypotenuse, that's the square root of 5 over 3. And cosine of v, let's go with the v setting, and cosine, which is also adjacent over hypotenuse, that is 4 over 5. And then minus sine of u, let's go back to the u triangle. And the u triangle sine, which is 2 over 3, well, that's actually a given quantity. That's a 2/3 times sine v, let's go back to the v triangle, and sine is negative 3 over 4. And we're ready to go with this calculation here. All right, the denominators for both will be a 15. Root of 5 times 4, that's simply 4 root of 5. And for the second term, careful. Negative times a negative equals to positive. And 2 times 3, that's a 6. 6 over 3 times 4. Wait, where did I get no, that's fine. 3 times 5, sine of v. Oh yeah, that's a 5 actually. So that'll be 4 root of 5 plus 6. The 6 is outside of the radical, everything divided by 15. And that's another example using the sum or difference formulas under different settings, for which we need to prepare some values here, some angles actually, before we can find the values of them. All right, let's look at last example for this section. That's the exact value of the tangent of 225 degrees. Well, so in this case, what time is it? 2:42. No, that's fine. I can make it. All right. So find the exact value of tangent of 255. There was a little typo here. It's not 225. It's 255 degrees. Well, the tricky part right here is to find the combination of angles that gives us nice angle, that is, angles that are from the unit circle that we already know. And well, for 255, have about, okay, tangent of 255, that's the same as saying tangent of, well, the result I have here have about 300 minus 45 degrees, and that's going to give us the 255 degrees. And well, both the 300 degrees, which is a special angle in the third quadrant, in fact I believe that's 4 pi over 3 in radians. That's a multiple of a 30-degree angle, I mean a multiple of a 60-degree angle, I believe. And 45 degrees, well, that's a pretty straightforward one, right? Well, here we're going to use the tangent formula. Let me write it down. Let me write it at the top so I don't scroll up to the first page. Tangent of u minus v, that's a tangent of u minus tangent v divided by 1 plus, that changes to a plus, tangent u tangent v. So that's a formula you have at the top of the first page in the handout. All right. So tangent u, that's a tangent of 300 minus tangent of 45 degrees divided by 1 minus or 1 plus tangent 300 degrees times tangent of 45 degrees. All right. Tangent of 300 degrees. Well, that's actually asking us to divide the y coordinate over the x coordinate of the point. So 300 degrees, which I believe, which is, well, actually it is in the third quadrant rather. That's y over x. That's a negative 1/2 and negative root of 3 over 2. All right. So in this case, oh no, 300 is in the fourth quadrant. Hold on. So that's positive 1/2 and negative root of 3 over 2. That's the 300 degree angle. And tangent, it's y over x. That's y over x. That's a negative root of 3 over 2 divided by 1/2. Divide out the 2's. And negative root of 3. Right here. Alright? So that's going to be negative root of 3 minus tangent of 45 degrees. 45 degrees has the value or has the point root of 2 over 2 comma root of 2 over 2. And well, the tangent function asks us to evaluate y over x. And well, in this case, root of 2 divided by itself, isn't that going to be just 1? So 1, and that divided by the quantity 1 plus tangent of 300, again that's a negative root of 3 times 1. Let's simplify this a little bit. Number 1, I'm going to factor out the negative in the numerator, put it outside, put it in front, and have these two terms as an addition of two terms. And then 1 minus the square root of 3. All right? And guys, this looks like we're done with this exercise. However, Alex may not like this as a final answer. It may ask you that your answer is correct, but it's not in the most simplified version. Because for this kind of answers, they may not like radicals in the denominator. So we need to rationalize the denominator for this expression. Well, how do we do that? Well, to rationalize the denominator, and actually we did a mini review of this like a few weeks ago. Let's refresh on that. We need to multiply by the conjugate of the denominator. So if we have a plus in the denominator, its conjugate, a minus, its conjugate will be the opposite in sign. That is a plus. So here is the thing. I know for the numerator we will have to FOIL these two. However, for the denominator you don't have to FOIL. Although if you want to FOIL, that's fine. Go ahead. However, check this out. This is a minus b times a plus b, which is the backwards version of a difference of squares, or the product of two conjugate binomials, which yields difference of squares. So for the numerator, let me do number 1. Negative for the whole thing, root of 3 times 1, that's root of 3. Root of 3 times itself, that's just 3 because we can cancel the radical. And then 1 times 1, which is 1. And 1 times root of 3, that's another root of 3. And in the denominator, instead of foiling and using the difference of squares formula, which by the way looks like this, that's a squared minus b squared, just go like this. Just do 1 squared minus radical 3 squared. All right? And simplify everything we have over here. So that'll be negative. Okay, root of 3 plus root of 3, that's 2 root of 3. 3 plus 1 equals to 4. And in the denominator, that's 1 minus root of 3 canceled with the square to give us a 3. And that's negative 4 plus 2 root of 3 divided by negative 2. And now, there's a couple of things that are going to happen. Negative over negative, that's going to become a positive, all right? And also notice how this 4, both the 4 and the 2, which is the coefficient of the radical, goes evenly with the 2 in the denominator. So that is 4 over 2, that's a 2. 2 over 2, that's simply a 1. So that's just 2 plus root of 3. Final answer.